All right, so test number 4, your last test of all the material for the semester, is finally over, right? So you should have completed all the assignments, hopefully. All right, so test 4 opened up this morning, and it is due by tomorrow at midnight. Make sure your volume is on mute. I was making out the test, and for this particular test, there aren't too many questions that I can actually choose from. In fact, there's only 13 questions on this test, but a lot of them have multiple parts, so don't let that make you worry and think, oh God, every question is worth 8, 10, 12 points or something like that. Some of them will be, but again, like I said, there's multiple parts for a lot of these questions. It's going to be similar to this quiz number 4 that I have posted up right now that you should be able to see it. I'm sharing the screen with you as well. All right, so we'll go through a few of these questions and you'll be able to see what you need to know for the test. Okay. All right, one other announcement is that the final exam is, I believe it's December. Let me not guess, let me look it up. Let's see where to go. December the 8th. Okay, so the final exam is comprehensive. It's going to cover everything you've had so far in the course. However, by the time you get to this point, you're going to see that the final exam is probably going to be your easiest test. Okay, because even to do this last test, test number 4, integrals and substitution rules and those kinds of things like that, you still have to know how to take a derivative. In this case, you have to know how to take the opposite of the derivative, the antiderivative, right? So a lot of this stuff is going to be just constantly cumulative, going one thing after another. You're going to see that once you get to even calculus 2. Okay, so this last section, chapter 5, is basically an introduction to calculus 2. Calculus 2 is going to be mostly all integration. Okay, so everything that we've done so far, now you're working backwards. Okay. All right, so does anyone have any questions before I get started with the review?
Well, do you do a review for the final?
Wait, I couldn't hear you. Kind of broke up a little bit.
Will you do a review for the final?
Yeah, I'm going to do a review for the final as well. In fact, I have in my math lab a final exam review for you guys. It's optional. It's not going to be towards your grade or anything, but you'll be able to, you probably, if I'm sharing my screen, you probably could see it right here. It's not available to you guys just yet because I want to do some tweaking to it. But the final exam practice test, so do that. You will do perfectly fine on your final exam. But we'll go over that too sometime probably next week before the final. And I'll send out that invite too. Let's see, it's on the 8th, so maybe on the 4th I'll schedule that so you get a couple of days ahead of time before we actually have to do the final. All right, so let's go. All right, again, I'm not going to work out all of these. I'm going to mostly talk more about them. A few of them I will work out. All right, so this is from the review. The velocity of an object moving along a line is given by, okay, on that particular interval from 0 to 4 for t, where t is seconds. Okay, divide the interval in 0 to 4 into sub-intervals. So 0 to 1, 1 to 2, 2 to 3, and 3 to 4. on each subinterval, assume the object moves at a constant velocity equal to the value of v evaluated at the midpoint, blah, 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 blah. Y'all can read, right? Repeat part A for n equals 8 subintervals. So you basically, by you creating these subintervals, you're creating little bitty rectangles. Let me show you what I'm illustrating here on my whiteboard here. Let's see. So we got 3t squared plus 2. Right, so that's a quadratic opening upwards. So I'm not going to draw it exactly to scale, but you have something like that. And from 0 to, say, 4. I know this is not exactly to scale, but let's just put it. And I'm going to divide this into 4 subintervals. So what you're doing...
We can't see what you're drawing.
It says share. I don't see this. Can you see it now?
Yes. Yeah, there you go. Now we got it.
I've got 2 monitors up, so maybe that's why. Can y'all still see the quiz, though? Because I just moved that to another.
I don't see the quiz. I see the drawing.
Just the drawing.
It's only on one screen that I can share. Okay. I got another monitor for so that I didn't have to have several open windows, but that's okay. All right, so to illustrate the point again, I'm basically, this is what's called the Riemann sum. Hopefully you watched the videos. There's several different ways to make this Riemann sum. If I start letting t equals 0, if I have t equals 0, I can find the y coordinate, right? Just by plugging it into the function. Okay? And by doing that, I would create a height of this rectangle and a width of this rectangle, right? Now this is what I'm using as a left Riemann sum right here, because I'm using left endpoints to get up to the graph. So this right here, if I'm at 1, to get up to the graph there, and if I make a rectangle from that height and this width, I get that rectangle. 2, I have this point here, make that one, and 3, I would have this point here. All right, so I have 4 different rectangles, and you know how to calculate length times width, right? Is area. So this area right here is 1 unit wide, right? By however high this is, if I would say this is my function, we had 3t squared plus 2. If I let t equals 0, the height right here is 2. If I let t equals 1, the height right here is, obviously this is not, of course I'm not to scale because that would not be 2. And this would not be 5. 5 would be higher than 2, right? If I let it be 2, 2 squared is 4 times 3, 12 plus 2, 14. Obviously my graph is not correct. That's 27, 29, and then 4, 16, 48, and 50. Oh, not using the right one. All right, so I've got all these heights right here. So all I do is do area of each one of these rectangles. This would be a 2. This would be 5 high, 1 wide. So that's 5. This would be 1 wide, but 14 high. 1 times 14. This is 1 wide and 29 high, and so forth. That'd be 29. So this is a left Riemann sum. Okay. Two ends. All right, so all I would do is multiply length times width to get each rectangle, and then add all the rectangles together and get the total area. Okay. Now, when you start subdividing this into more intervals, you're going to get more rectangles. The rectangles will be shorter in width, right? and you can still calculate their heights, but now you'll have a lot more rectangles to add up together. And it's causing a little bit more accuracy of the amount of area that falls under this curve. You can see intervals 1 and 2, the first two intervals right here, when we created our rectangles, went above the curve, right? The other two, 2 to 3 and 3 to 4, the rectangles went below the curve. So the 2 to the left overestimated the amount of area, and the 2 to the right underestimated the amount of area. So they're kind of negating each other a little bit right there. So it's kind of giving you the total area under the curve is somewhat accurate. But again, like when you start dividing this up into more and more rectangles, you get little slivers of rectangles under the curve, or perhaps even over the curve or something. But you get a lot more accuracy with that. All right, so you can do right Riemann sum. Do a quick sketch of that. If I do 1, 0 to 1, instead of going 0 up to the function, I use the right of 1 first up to the function and create a rectangle. And then the 2 up to the function and create a rectangle. The 3 up to the function and create a rectangle. See, in this one, the last two are above the curve in this particular case. That all depends what the function is, with whether you can be above or below for certain intervals. So it's the right Riemann sum. Then you got your midpoint Riemann sums. Those are more accurate. Okay, so instead of going from the endpoint 0, 1, you pick right in the middle and go up to the graph. So if I've got 0 to 1, I'm going to pick 1/2 and then go up to the graph. I'll have a rectangle drawn like this. Portions outside, portions underneath. And then if I've got to 2 there, and then I use those midpoints to determine what the height of each rectangle will be, and then sum up each rectangle. So the midpoint Riemann sum is your more accurate one, and you probably got through that through the lectures. And so what the idea of all this is you create an infinite number of subintervals. So you have an infinite number of rectangles, which now gives you a bunch of length times widths. Add them all up, summations. You've probably seen that to come. And then that would give you the total area under the curve by adding up all those individual rectangles. So that leads to what's called the integral. So here's a little bit more for this question, exactly what I was just talking about. Okay. Sketch the graph. Okay. So the graph is 2 over x plus 2. So you find the right one. Let me just show you the answers. 1 over x plus 1 is changed. Okay, so obviously you put this in the graphing calculator if you needed to match up the correct graph, or you could pick some points for x and draw it by hand. You're only on a specific interval from 1 to 6 with n equals 5, so 5 partitions. All right, illustrate the midpoint Riemann sum, and then calculate it. So exactly what I just did. Use the midpoints of each one of your intervals. Okay, that's going to be evaluated into the function to determine the height of the rectangle. Okay, and then you have your length times width for each one of those rectangles and add them up. All right, summations. These are not too difficult to work out by hand, but let me show you, if you have a graphing calculator, how you could do this. It is really easy. All right, so like part A should be obvious. That's pretty easy to do. This is a summation where k begins at 1 and ends at 13. Okay, so this k equals 1 to 13. Those are your indices. Okay, so it means start with 1, then add 2, then 3, then 4, then 5, all the way to 13. So the sum of 1 through 13 is what that is. Now your calculator has this feature. If you go to the math button, and you scroll down, you will see summation right there. Now hopefully you have the 84 calculator. If you do, the 84 calculator, you'll see exactly the summation notation. And all you do is fill in the blanks. Now you don't have a variable k in here, but in the calculator you have the variable x. So we're going to say x goes from 1 through 13. So you just arrow over and just fill in the blanks. And this is not k, it's x. And when you hit enter, there's your answer. It's 3091. If it's a little bit more complicated, let's do G. K is 1, so x goes from 1 through 6 of x times 6x plus 7. And we close that parentheses and just realize the automatically opens up a parentheses for everything that is the function that is being summed. So make sure you close it off at the end as well. And when you hit enter, 693. So that easy. Now the ones that involve trig functions, sometimes the evaluation of a trig function for a specified angle, use those exact values, like square roots of 3 over 2, square roots of 2 over 2, sometimes like that. If they wanted an exact value, for this one you got 0, it just how happened you get 0 for it, and works out nicely. But it could have been some kind of other answer that involved fractions or radicals. Your calculator won't necessarily show the fractions, and it definitely won't show the radicals as your answer. So you may have to do those by hand. So basically just write each term out. So from 0 to 7, there will be 8 terms, right? So just add them all up. All right. All right, here's another Riemann sum kind of problem. All right, I'm going to skip over that one. All right, this one says just use geometry. Okay, this is fairly easy. In geometry, all you're doing is looking at areas of rectangles and perhaps triangles. So here's the correct graph, and we want to figure out what is the area from -5 to +7. All right, so -5, wish I could make that bigger. Let's see. All right, so -5, 1, 2, 3, 4, 5, and goes down to here. Looks like that would be, looks like every tick mark is worth 3. 1, 2, 3, 4, 5, 6, 8, 9, 10. Yep, 3. So that would be right there. So that'd be a -24, right? So the portion of the triangle below the graph, below the x-axis, is actually 6 units wide. To get to -5 and see where the x-intercept is 6 units wide, and then 24 units down. So you could do area of a triangle is 1/2 base times height, right? So you calculate the area of that. 1/2 of 6 is 3 times 24, 72. So that's the area of this bottom triangle. And then you go from up to 7. So you go to 7 over here and do the same thing, calculate its height. Let's see, 7 would be right there. Calculate its height. Its height is also 24. Okay. but it's only 6 units wide because go from the x-intercept. So from 1 to 7 is 6 units wide. So it's the same exact thing as the bottom down here. So half of the base, half of 6 wide is 3 times the height of 24 is also 72. Add those two areas and you get 144. So the whole concept of this right here is to get you prepared to see the integral that's coming up next. So it's the same idea, area under the curve. All right, so this is just some fancy notation. The limit as my delta, my change, right? And that's what a delta is. Approaches 0. So my change is basically minimal, right? So it's approaching 0. So my intervals basically, that's what they're doing, making many intervals of your changes in x. So it's going to 0. So the width of each one of these rectangles is so small, okay? And you're going towards infinity, right? So k goes from 1 through n in this case. We don't know what n is in this specific value just yet. But we have some x sub k star, which means this is more likely the midpoint of each one of these intervals. It gets cubed, okay? That's going to determine the height. So this just first factor right here, x sub k star cubed, that determines the height. That is the actual function, right? For given values of x, times the change in x. This is your width right here. This is your height. This is your width. When this interval. All this means is now we have a new notation using the integral sign. So now the lower integral, lower bound, this is 7 and goes up to 13 of the function, which is x cubed dx. Dx means change in x. So the x cubed right there is your height. Dx is your width, your change in x. So it's the same exact thing right here. So now we have a shorthand way instead of calculating these really intense summations is to use the integral sign. All right, another geometry problem, just figuring out areas. Nobody should miss these. This is very straight up. You're not going to have any complex functions. They should all nice be linear ones. Anything that's curvy using geometry, we only know formulas for squares and rectangles and triangles and perhaps circles, right? We might be able to do that one. But anything else that's complicated, you got to break it down into variations of rectangles and triangles and those things. Like see right here, break it down into a rectangle and a smaller triangle and figure out those two specific areas. All right, so they give you the actual values of the areas for each region. So all you're doing is now answering the question using the integral notation. X goes from 0 to 2 pi of this function. How much is that area? So go from 0 to 2 pi, sum it all up. Area 1 is, R1 is 1, R2 is pi minus 1, and so forth. So just add them all up. All right, so here is some actual integration. I'm going to work, let's see. You could do these by the methods that you should have learned by now, or you can just kind of intuitively think about what this would do. All right, so let's just pull up my whiteboard and we'll work it out. All right, so part A. All right, so we're given one interval, I, is from 0 to 3 of x cubed minus 2x dx is equal to 45/4. Part A. If I go also from 0 to 3 of now, notice we have 12x minus 6x cubed dx. Notice you could take something out, right? If I would take out, let's just do the 6. We're left with, actually, let me take out -6. -6 times 2x. Actually, let me just keep it +6, sorry. I'm trying to make it look more like what was given. So taking out +6, 6 times 2x is 12x, and 6 times -x cubed. Actually, I should have put up -6. I'm looking at the wrong one, sorry. Let me just erase this. There we go. I want to end up with a +x cubed, right? So to take out, get a +x cubed, I'm going to take out -6. -6 times -2x is +12x. -6 times +x cubed is -6x cubed dx. And you can see if you just rearrange these two right there. And also, this is a constant. A constant as a factor into the function can come out of the integral. So this is -6 times the integral from 0 to 3. And this right here, I'm going to rewrite, put it as x cubed first, and then minus the 2x dx. And using your properties of integrals, that the first one is 45/4. -6 times that. That will give you the -135/2. Okay. So that's how you do that one. Now you can see 2x minus x cubed. Okay. You can take out the negative. Okay. But notice your integration went from 3 to 0. When you do that, you take the negative integral of it. So the negative of the negative now is a positive, so why you get the same thing. Okay. So if you're going to swap your limits of integration, so you went from 0 to 3 in the beginning, now at the bottom it's going from 3 to 0. You're going backwards, right? So when you're going to go backwards like that, you negate it. So you put the negative integral on it. And then the factor of -1 comes out to be equivalent to the original. So that's going to evaluate to just -45/4, and then you throw the negative in front. The integral negative of the negative still gives you the positive. So that's just some rules of integration, little tips and techniques. If you didn't know that, you can actually just use the fundamental theorem of calculus, which is extremely important, which we'll do some of those in a second. All right, here's some more just notation-wise. Find a prime of x. Okay, so you're trying to figure out what the actual function was. The antiderivative, that is. Find the area of the region bounded by the graph. Okay, so area of the region is the integral, so you can rewrite this. Okay, so what you have to do for these, graph it, see if the graph is above the x-axis or below the x-axis, because anytime you're going to use the integral sign, okay, that can possibly mean, that's supposed to be a straight line, sorry. So if I have a graph, let's just say, that is like this, and if I say, let's go the integral from 1 to 5, well, if I do the integration from 1 to 5, whatever my function may be, it's going to give me a positive number, right? So it's positive here. If I do say from -3 to 5, this is going to give me net area. Okay, so net area, some portions of below the graph can cancel out portions above the graph. Okay, so you got to watch out for that. So what you're going to have to do is see where the intercepts occur and do individual intervals. So say this interval, this x-intercept is at -1, let's just say. I would do the integral of -3 to -1 of f of x. And I'll probably get a negative number, right? But I'm going to take the absolute value of that. Okay. So that way it gives me my positive area here. And then I'm going to do plus the integral from -1 to 5. And if that's all above the graph, I'll get a positive number. Still taking its absolute value. So I'm just taking absolute values of portions below the graph and above the graph and adding them all up. All right, so for this one right here, x squared minus 45. Let's see. I'm going to use my graphing calculator. Well, we don't need to. I could graph it by hand really quick. I'll have to change all kind of window dimensions to do that. X squared is a parabola opening upwards, right? And it goes down on the y-axis to -45. So we're something like this. If I set this equal to 0, y being 0 would give me the x-intercepts. So x is equal to plus and minus the square root of 45, which is what? 6 point something, almost 7. I can use calculator if I want, but that's good enough. All right, so this is at -6 point something. This is at positive 6 point something. And I'm looking from -1 to 2. This is solely below the x-axis, right? So I know just from this graph right here, if I do the integral from -1 to 2 of x squared minus 45 dx. All right, so here's the fundamental theorem of calculus. First, I'm going to take the antiderivative of this. Remember, the antiderivative is the opposite of taking the derivative. The derivative, normally you would say 2 times x, reduce the exponent, right? By 1. We're doing the opposite here, an antiderivative. I'm going to do x, bump up the exponent by 1, and divide by that new exponent. And then minus 45x. That's your antiderivative, right? If I didn't have limits of integration here, -1 and a +2, I'd add a plus c. But I have limits of integration. So this says take this right here and evaluate it at the upper limit and at the lower limit and find their difference. So let's do that. So this is going to be, when I put 2 in there, 2 cubed over 3 minus 45 over 3. That's the first evaluation, minus the second evaluation, -1 cubed over 3 minus 45 times -1. All right, so this is 8/3 minus 135 minus, this is -1/3 And that's negative 45 times negative 1 is positive 45. All right, so we got 8/3. This is 8/3 plus 1/3, right? Is 9/3, which is 3. Negative 135 minus 45. That's negative. Oh, let's see, I got an error here. Oh, I see what I did wrong. I put in a 3 right here. That should be a 2. That should be a 2. We're evaluating 2 into there. For some reason, I was looking at a 3. So that's negative minus 90. All right, so negative 90 minus 45 is negative 135. And there is your negative 132, but we take the absolute value because we are under the curve. We want positive area of 132. So this is the fundamental theorem of calculus. I can tell you on the test, I will ask you to show some work like we have been doing in the past. Certain questions will require you to show some work to be uploaded into D2L. There'll be very few problems you have to actually show work on, but this is one particular one I would ask you if it does say evaluate the integral or something like that. I would say show your work definitely using the fundamental theorem of calculus. Okay, so a lot of the stuff you can do with a calculator or a photomath or one of those things. I don't want that. I want you to see actual work for these particular ones. Because if you're just relying on that stuff and you got to take calculus 2, I promise you, you will not pass calculus 2. All right, so I'm just trying to prepare y'all for what's to come. All right, so here's some more integration. Now, when the function is a lot more complicated, meaning you're seeing a lot of exponents in there, kind of reminds you a little bit of the chain rule, right? Well, the chain rule was a composite function, right? You use finding derivatives of composite functions, we get to use the chain rule. So we have functions within functions, but we didn't know exactly what those two functions were composed of, right? So going backwards is really hard. So I need to figure out, how do I take the antiderivative of this? Well, this is using substitution. There's a few different methods to do this. I'm not exactly sure of how the author described it to you in the videos, but most people use the same techniques. It's just their approach to it might be a little different. But if I have, this is an indefinite integral, so it means I don't have limits of integration, so my final answer will be just an antiderivative plus a constant c, right? So let's show you how to do this. They're already telling you what to use as a substitution. So they're saying let u equal the x squared plus 5. Now there will be points to where you won't know or won't be told what to use as a substitution. I mean, this is just kind of preparing you to what's to come too as well. But the hint right here is the part that's in the grouping symbol, the x squared plus the 5, that's typically the part you use as your substitution. All right, so if I have u is given as this, I want to find the derivative with respect of u with respect to x. So this is the notation you use. The derivative, this is Leibniz notation, du over dx, right? This is u prime, right? So if you keep this notation, watch how easy everything will be. All right, so u prime, du over dx, is equal to the derivative of x squared is 2x, and derivative of 5 is 0, right? So now we got this little fraction equal to 2x. I want to solve this for du. So du, all we do is cross multiply. Du is equal to 2x dx. Right, so now you can see this entire integral right here can be rewritten with terms of u instead of x's in there. So right here, I'm going to highlight in red, this is u. And then let me put it in, let's do green. It's Christmas. 2x times dx. 2x times dx is du. This is du. So this entire integral is now in terms of u, the integral of u to the 8th du. That's really easy, right? To find the antiderivative of u to the 8th. Antiderivative of u to the 8th is u to the 9th over 9. Plus some constant c, right? Now I have to go back in and say what was u. U was x squared plus 5. So x squared plus 5 to the 9th over 9 plus c. Right, there's our answer. You could leave it like that, or you could take out the 1/9 and throw it out in the front like they did there. It should accept either way. Yeah. So that substitution, that is, if you were to try to find the antiderivative of this, the only possible way you would be able to do that is to put it into its total polynomial format, to where you would have term plus term plus term plus term. Now this would be rather long, right? Because it's raised to the power 8. So you have to multiply x squared plus 5 times x squared plus 5 times x squared plus 5, 8 factors of that. FOIL it out, keep on distributing. Eventually, a lot of things will cancel and combine together. So substitution makes this really easy. Okay. There's another one that tells you what to use as your substitution. All right, so this one, it doesn't. Let me show you. After you do a handful of these, you'll get the idea of what to use as your substitution. All right, so one thing about e to the x is derivative is e to the x, right? But this is a little bit more complicated than e to the x. It's e to the 3x minus 5. So that you got to throw in something else in there, right? So we have e to the 3x minus 5 dx. If it was just e to the u, antiderivative is also e to the u, because this derivative of e to the u is e to the u, right? So we want this right here to be u. So I set it up, u is equal to 3x minus 5. The derivative of u with respect to x, du over dx, this derivative of this is just 3. Then if I cross multiply, I solve for du is equal to 3 dx. All right, so if I let that be u, I need dx right here, and I need a 3 in there, right? So easy way to compensate for that is multiply something by 1, it's still 1, right? If I multiply something by 10 over 10, that is equal to 1, right? So what I'm going to do in here, I have a 3, I'm going to multiply and divide. So 3 over 3, I'm going to insert into this problem. So I have e to the 3x minus 5. I can put a 3 there, it doesn't matter. Doesn't matter where you put a factor in, right? You can put it in the front, put it in the back, it doesn't matter. All right, so now I make my substitutions. Notice I have 3 dx right here. This is du. And I have this right here, it will be u. So I'm going to rewrite this as the integral of e to the u. Let me do this real quick. I'm going to move All right, so we got 1/3 right here as a constant, right? So put the 1/3 in the front. 1/3 times e to the u du. 1/3 can come out of the integral if you want. And the antiderivative of e to the u is e to the u. So this is 1/3 e to the u plus some constant c, and then we go back and substitute what was u, 3x minus 5. I know some of these you just kind of start recognizing patterns. Try to avoid that because the more complicated it gets, you're not just going to be able to say, oh, let me just throw in a 1/3 here or something like that. Because the way my math lab will have this, if I hit a similar problem, you'll have e to the probably 7x plus 2 or something, e to the 5x minus 1, something like that. So you kind of see the pattern in there. It's just the derivative of the inside and take its reciprocal, the derivative of the exponent, that is, and the reciprocal of that gets thrown out in the front. But again, try not to memorize patterns, kind of realize what's going on to come up with the answer. All right, so this one's just using some trig functions. So this says use a change of variables or the table to evaluate the following indefinite integral. Excuse me for a second. So if you look at the table of integration values, you can use this. This is kind of a little bit of an intro to what's to come in pre-calculus, and believe me, there's a lot more than these. So you can kind of figure out which one's going to match up, and then you evaluate it. So you got a cosine of 9x, so you can find, this is that very first one right here. It's going to be 1 over a, so you match up 1 over 9, and then sine of ax plus c, and then you have to evaluate it, right, using the fundamental theorem. And when you do that, it all comes out to -1/9. So a lot of these tables right here, you're going to use in in calculus 2. So you're going to have to get very, very familiar with a lot of these. In fact, most of these you're going to have to memorize them. Okay, and believe me, it looks overwhelming, but you're going to do it so often enough, you're going to start recognizing the format, and you're just going to memorize. Oh, I know what that one is. So. All right, so this one's just, it's an integral as well, okay? Area under the curve, basically that it is, right? So x minus 5 out to the 4th between x is 4 and x is 6. So again, you can figure out where the intercepts would occur for this one, okay? You can kind of draw a little bit of a graph or use your graphing calculator to give you a better idea. This probably would be best to use a graphing calculator sometimes and see if the graph is totally above the x-axis or split, some below, some above, all below. So you'd have to, let's do that real quick. Calculator. So I would put this into the graph, x minus 5 out to the 4th, and graph it. All right, so we're looking between 4 and 6. If you even want to highlight this part to zoom in to see if that part is all above the graph or not, let's see. I'm pretty sure it is. I'm gonna do a box. Pick a corner and make a box like that. And yeah, I'm pretty confident we're above the x-axis. If you put this even algebraically to figure out where the x-intercepts would occur, if there are any, we've got x minus 4 or x minus 5, x minus 5 to the 4th. set that equal to 0. That's going to give us the x-intercepts when y is 0. So if I take the fourth root of all that, right? Fourth root of 0 is still 0. X minus 5, x equals 5. We have an x-intercept. However, it just touches the graph at 5. So that graph right there, it's something like that. Boom, touched at 5. And maybe you recall something from pre-calculus about intercepts and their degrees. X to the fourth right there means you touch the graph. If this is even, it touches the graph. If it was odd, it goes through the graph. If it's even and they all point up in the same direction or all down in the same direction, it's where it's in behavior. But this is at 5, and we're trying to find the graph, the area between 4 and 6. So all I got to do is integrate that function between 4 and 6. So 4 to 6 of x minus 5 out to the fourth dx. All right, so you got to use a substitution because it's x minus 5 out to the fourth. Okay, so we're going to let u equal x minus 5. Therefore, du over dx, derivative of that is 1. Therefore, du is equal to 1 dx. We have that there. 1 dx is 1 dx. This is u. All right, so now this is a definite integral because we're using limits of integration, 4 to 6. But this is x, right? I need to change that. We're turning this into u. So I'm going to have u, if x is 4, 4 minus 5 is negative 1. 6 minus 5 is positive 1. So these are u values when I make my substitution. And now I have, now you can use your properties from, you can say negative 1 to positive 1 on a function of x to the fourth. This is symmetry, right? So you can use from 0 to 1 if you want and then double it, or you can just use the fundamental theorem and evaluate the 1 and the negative 1. So this would be u to the fifth over 5, right? Evaluate it at 1 first and then at negative 1. That's not too hard. So putting 1 in there is 1 to the fifth over 5 minus negative 1 all to the fifth over 5. So that's the fundamental theorem right here. So 1 to the fifth over 5 is still 1 to the fifth. This will be negative 1/5, so minus a negative is plus. So that's where you get the 2/5. So watch out for those. Anytime you're going to do substitution on a definite integral, your limits of integration need to also change. Okay. All right, so that's the end of that particular test review. So hopefully I gave you enough information to where you should do pretty well on this review as well, on this quiz. And so if you do well on this, there's no reason you shouldn't do well on the test as well. So exit out of this. Stop sharing. All right, so again, your exam, I believe, only has 13 questions on it, 12 or 13, something like that. So you got plenty of time on it. Make sure you pay attention to any little, you know how my math lab is. There's a little tricky directions sometimes, how to enter your answers, okay? I will tell you this too. I mean, you have your graphing calculator. Use it if you want to. I can tell you if you have the 84 calculator, I'm not going to know if you're doing this or not, but at least you'll be able to check some of your answers for your integrations. Under the math button, option 9 right here. Wait, y'all can't see this. Let's share. All right, so hit the math button and go to option 9. It's function integrate. There's a definite integral right there. Okay. So if you know some limits of integration, like we just had, if I had that last one, x went from 4 to 6 of, it was x minus 5 to the 4th. Dx. The only thing bad about this, if it's asking for area, like that particular problem just asked for, it was area, right? So the only way this is going to calculate the exact answer that you're going to see is knowing if the graph is totally above the x-axis. Okay, if it's not, if the portion's above and below, it's going to give you net area. So some parts below will cancel out parts above. So you got to watch out for that. But if it's just an integral and asks you to evaluate it and not asking about areas, it just says evaluate. You can type it in, boom. And then you say 0.4 if you want to change that back to a fraction. It's 2/5. Okay. So use that as a feature to check your answers and some of the stuff. A lot of this I still say show your work, so you need to go in and show some work by hand and upload those to D2L. But if you have the 84 calculators, you have this feature. I'll show you another trick too in math you may have not known about. In derivative. Need a clear screen. Quit. There we go. This says take the derivative with respect to x of the function. Let's just do something easy. Let's do 2x cubed. So you know the derivative of 2x cubed, that would be 6x squared. And let's say if I evaluate x to be 6x squared, that's 4, that should be 24, right? Now, why am I seeing 0.00002? Because you know your calculator is an estimator, really. Okay, so your calculator has a finite number of numbers in it. Okay, so you know what the derivative mean is. The slope of that tangent line is approximately equal to the slope of the secant line, right? So the secant line values are getting closer and closer and closer. So you have to interpret this to be equal to 24. Okay. And if I do it again, I might get some other number. Watch, sometimes it changes. No, it's still giving me that. Okay. But you can assume that's 24. Okay. So that it's not going to tell me exactly the function of what the derivative is. It's going to tell me a derivative evaluated at some value. Okay. So that's another little tip if you have to evaluate a derivative sometimes. All right, any questions before we end? Will I send the video through a YouTube link? Yes, I will be doing that again. For some reason, Webex decided to change up their format to where it used to be saved as a WRF file. Now it saves it as I think an MP4 file. And these MP4 files are too big just to send through an email, so I have to upload it to a YouTube video. And then I'll share that link with everybody. Okay, so I'll post that shortly as well. All right. Let's see, anything else in the chat? All righty. Well, if y'all don't have anything else, we'll end this, and I'll send out that video later on this afternoon. I say this afternoon, it'll probably be within a half hour or so. But good luck to everybody on the test. Hope everybody enjoyed their semi-short break. It was nice. Thanksgiving week last week, right? So just hang in there. Just 2 more weeks left, right? This week, and then next week is starting the finals. So hopefully everybody's nerves aren't as rattled. All right, and I hope everyone does really well on the next test. And I will chat with y'all later. Look for another email coming out later on about an invite for a final exam review. All right, y'all have a great day.
Thank you.
Bye.
Have a good day.
Cheers.